Hello students, this is the fifth and last part of our chapter Gravitation. In our previous part, we have studied about the relationship between acceleration due to gravity on the surface of Moon and on the surface of Earth. There we have studied that the value of acceleration due to gravity on the surface of Moon is 1/6 the value of acceleration due to gravity on the surface of the Earth. Also in our previous part, we have established equations of motion for free fall. In this part, we will study about mass and weight of an object and also solve some numerical problems. So first let us start with mass. So students, what do we mean by mass? Mass is the quantity of matter contained in a body, or we can say the contents present within a body. In order to understand it, let us take two objects. Here we have object A and object B. If you carefully observe these two objects, then you can see the dimension of the object is same. The dimension of these two objects is same. But first, let us count the contents present in these two objects. So when you count the content present in object A, then here 1, 2, 3, 4, 5, 6, 7 and 8. There are 8 contents, or you can say 8 particles present in the object, or you can say the object A is consisting of 8 particles. In the same way, let us count the content present in object B. So here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So we can say that object B is consisting of 12 particles, or there are 12 contents present in the object B. So as the dimension of these two objects are same, but here it is clear that contents present in B is more than the content present in A. Or we can say object B is consisting of more particles as compared to the object A. That is, quantity of matter in object B is more than quantity of matter in object A. Hence we can say that mass of object B is greater than mass of object A. So it is clear that mass is the quantity of matter contained in a body. Mass is measured with the help of quantity of matter contained within a body. Now let us take a situation. Let us take one more situation to understand it more clearly. Here you can see that this is our Earth and this is the Moon. And on both these surfaces, the same object is placed. And you know, this object is consisting of some matter, and that matter gives the mass of this object. So first let us reply this question. Will the mass be different in these two cases? And in order to answer this question, first reply this question. Will the amount of matter in the object be different? Is it possible that when this object, which is placed on the surface of Earth, is placed on the surface of Moon, then the amount of contents present inside this body is going to change? No. It is very clear that the amount of matter inside this object is not going to change. So we can reply the answer of first question, that is, will the mass be different in these two cases? So the answer is no. The mass in these two cases are not different. The mass of the object remains the same. Why? Because the amount of matter in the object is not going to change. Either we place it on the surface of Earth or on the surface of Moon or anywhere else in the universe. So from this example, it is clear that the quantity of matter in an object is same everywhere, whether it is on the Earth, the Moon or anywhere else in the universe. It means mass of the object is same everywhere or constant everywhere. Okay. Again, mass is a scalar quantity because it has no direction. It has only magnitude. and the SI unit of mass is kilogram. So students, it is clear to you that mass of an object remains constant. Does not matter where it is placed in the whole universe. Based on this result, we can say that the gravitational force between two objects remains the same, irrespective of where these two same objects are placed. Means either they are placed on the surface of Earth or on the surface of Moon or anywhere else in the universe, keeping the same separation between them. Then the gravitational force between them will remain same. Let us understand it. How? Suppose there is an object of mass capital M. Now we take one more object in front of this object. Suppose the mass of this another object is small m. And again the separation between their centers is small r. Now students, according to universal of gravitation, you know that whenever there are two objects separated by a certain distance, then there is a gravitational force acting between them. And this gravitational force is directly proportional to product of their masses and inversely proportional to square of distance between them. Suppose in this case, the force of attraction acting between these two objects is capital F. Then, according to universal of gravitation, we can calculate the value of F as capital G into product of masses, that is capital M and small m, divided by square of distance between them, that is r. So we have the formula for the force capital G capital M into small m divided by r square. Now students, let us understand here. Here you know that the capital G is the universal gravitational constant, which is constant in the whole universe. It means from this equation what we can say, the force is proportional to capital M. This force is proportional to small m, and this force is inversely proportional to 1 upon r square. So wherever we take these two objects, keeping the separation between them same, either we take this two objects on the surface of Earth or on the surface of Moon. So what happen? Will the force will change? Will the force is going to change? No. The force is not going to change. Why? Because you know mass is constant everywhere. Capital M is not going to change. Small m is not going to change. And also we have maintained the same separation. It means r is also not going to change. So if all these three factors are constant, then how the force is going to change? So it is clear that the gravitational force of attraction between two objects remains the same wherever we take these two objects, keeping the separation between them as same. So I hope it is clear. Now let us move to next slide. But before that, let us understand mass of a body can never be zero. Why? Because you know mass is the measure of quantity contained within a body. And everything in this universe is consisting of some matter. So if everything has some matter, then we can say that mass of a body can never be zero. The next point regarding mass, we have the mass of an object is measure of its inertia. Students, in chapter 2, we have studied about inertia. Inertia is the tendency of an object to maintain its state of rest or of uniform motion. Suppose there is a truck and there is a bicycle, which you can move easily. Probably your answer will be cycle. You can move easily by applying some force on cycle. Why? Because the mass of the truck is very much large as compared to mass of cycle. That's why it is difficult for you to change the state of rest of truck as compared to cycle. Means inertia of truck is more as it has more tendency to maintain its state of rest because of its large mass as compared to cycle. So it is clear that mass of an object is measure of its inertia. Now, mass of a body can be measured by the use of a beam balance. So this is the beam balance. In beam balance, we measure the mass of an object with the help of comparing it with some standard mass. Here you can see that there are two identical pans which are supported or suspended with the help of a beam. And there is a pointer. Now what happens? Whatever mass we have to measure, we just put it on the right pan, while on the left pan we put the standard mass. Now pointer starts moving either to the left or to the right. When the pointer becomes stationary or exactly vertical position, then we can say the mass on both the pans are balanced and we can measure the mass of the object. Now students, let us understand what is weight. So in general, weight is defined as measure of gravitational pull on an object. Means the strongly the gravitational pull acting on an object, the more the weight will be. Let us understand it with the help of an example. Here you can see that this is the surface of Earth, and again let us assume this is the surface of Moon. Okay. The acceleration due to gravity on the surface of Earth is GE, and the acceleration due to gravity on the surface of Moon is GM. Let us place same object of mass small m on the surface of Earth and also on the surface of Moon. These two objects have the same mass. Now, if we calculate the gravitational force acting on this object due to the Earth and Moon. So here let us say the gravitational pull is F1, and this F1 is equals to mass into the acceleration due to gravity GE. In the same way, the gravitational pull acting on the same object due to the Moon surface is, let us say this is F2, and this F2 is equals to mass into acceleration due to gravity GM. Okay. Again students, you know that the acceleration due to gravity GE, that is on the surface of Earth, is 6 times the acceleration due to gravity on the surface of Moon. From this relation, we can say that the force F1 is equals to 6 times the force F2. It means the gravitational pull acting on the same object due to the Earth is 6 times stronger than the gravitational pull acting on the object due to Moon. And if the gravitational pull is more, then we can say weight of the object on the surface of Earth is more as compared to weight of the object on the surface of Moon. So I hope it is clear to you that weight is defined as how much the gravitational pull acting on an object. Now, let us see one more situation. Here you can see that there are two places, place A and the place B. The gravity on place A is x units and the gravity on place B is 2x units. Again, the same object of mass small m is placed on these two surfaces. Then here we can see that if the gravitational pull acting on the object due to the place A is x units, then the gravitational pull acting on the same object due to the place B is 2x unit. It means it is 2 times stronger as compared to the gravitational pull of the place A. Or we can say the weight of the object on the place B is 2 times more than the weight of the object on the place A. So I hope students it is clear to you that what is weight. In the same way students, we can define weight of an object on Earth is the force with which it is attracted towards the earth. Okay, let us suppose there is an object of mass small m and g be the acceleration due to gravity at a given place. Then according to Newton's second law of motion, we know that force is equals to mass into acceleration. Here the mass is small m and acceleration is equals to acceleration due to gravity, that is g. So we can write the force capital F equals to mass m into g. Let us say this is equation number 1. Again students, here we have defined weight of an object on earth is the force with which it is attracted towards the earth. So this is the force with which the object of mass m is attracting towards the earth. Hence we can say this force is equal to weight of the object. And weight is represented by capital W. So in equation 1, we can replace the force F by weight W. Then what we get? W is equals to m into g, where W is the weight of the object, m is the mass of the object, and g is acceleration due to gravity. Hence we can write weight of the body is equals to mass of the body into acceleration due to gravity. It means if we are calculating weight of an object on the surface of earth, then what we do? We multiply mass of the body into acceleration due to gravity on the surface of earth. If we are calculating weight of the object on the surface of moon, then we put mass of the body into acceleration due to gravity on the surface of moon. So I hope it is clear. Again students, weight is a force and you know the SI unit of force is Newton. Hence the SI unit of weight is also Newton. Okay, and if this is a force, then it means it is a vector quantity having both magnitude as well as direction. So what is the magnitude of the weight? This is the magnitude of the weight. We calculate magnitude of weight just by multiplying mass of the object and acceleration due to gravity on that surface. And the direction of weight is vertically downward towards the center of the earth. So I hope students it is clear to you. So this is the required formula for weight of an object. Now students, sometimes weight is also expressed in kilogram weight. A kilogram weight is the weight of an object of mass 1 kilogram. Or you can say it is the force acting on an object of mass 1 kilogram due to gravitational pull of earth. So we can write 1 kilogram weight is equal to weight of an object of mass 1 kilogram, and weight of an object of mass 1 kilogram is equals to mass, that is 1 kilogram, into acceleration due to gravity g. Now 1 kilogram into g is replaced by 9.8 meter per second square, because you know value of acceleration due to gravity on the surface of earth is 9.8 meter per second square. Again it is equals to 9.8 kilogram meter per second square, and kilogram meter per second square is also known as Newton. So we can say 1 kilogram weight is equals to 9.8 Newton. Again students, like kilogram weight, there is one more unit, gram weight. Gram weight is defined as the force acting on an object of mass 1 gram due to the gravitational pull of earth. Let us write 1 gram weight is the force on object of mass 1 gram due to gravitational pull of earth. Okay, so I hope the definition is clear. Now let us derive the value of 1 gram weight. Now let us see. Here what we write, 1 gram weight. 1 gram weight can be written as 1 upon 1000 kilogram into G. It is equals to 10 to the power minus 3 kilogram into value of G is 9.8 meter per second square. Okay, so it is equals to 9.8 into 10 to the power minus 3 kilogram meter per second square, or we can write it as 9.8 into 10 to the power minus 3 Newton. Okay students, it means 1 gram weight is equals to 9.8 into 10 to the power minus 3 Newton. Now let us convert it into CGS unit. So what we have calculated, 1 gram weight is equals to 9.8 into 10 to the power minus 3 Newton. Again students, from our previous chapter, you know that 1 Newton is equals to 10 to the power 5 dyne. 10 to the power 5 dyne, where Newton is the SI unit of force and dyne is the CGS unit of force. So we can write 1 gram weight is equals to 9.8 into 10 to the power minus 3 into, in place of 1 Newton, what we can write, 10 to the power 5 dynes. So let us write 10 to the power 5 dynes. So here 10 to the power 5 and here 10 to the power minus 3. So what we have, 10 to the power 2. So 9.8 into 10 to the power 2 dyne, which is equals to 980 dynes. So 1 gram weight is equals to 980 dyne. Now students, you know weight of a body is given by W equals to m into G, where m is the mass of body and G is the acceleration due to gravity. Again you know that mass of body is remains constant. It will never change. Hence, from this equation we can say that the weight is directly proportional to acceleration due to gravity. This expression means that if the acceleration due to gravity is increasing, then weight will also increase. If acceleration due to gravity is decreasing, then weight will also decrease. Now let us understand how the weight is affected with the help of acceleration due to gravity. In our previous video, we have learned that the value of G is minimum at the equator and maximum at the pole. It means at equator, the value of G is decreasing. And if G is decreasing, then we can say weight is also decreasing. And at poles, the value of G will increase. So if G is going to increase, then weight will also increase. That's why a body weighs more at poles because of more value of G than at the equator. Now again you know value of G decreases with height. As we go above the earth's surface, value of G is going to decrease. And if the value of G is going to decrease, then weight will also decrease. So that a body weighs less on mountains than at the plains. And again we have learned the value of G is 0 at the center of the earth, because as we go deep inside the surface of earth, the value of G is going to decrease, and at the center of the earth it becomes 0. So from this equation you can see W is equals to m into G, and at the center of earth G becomes 0. So what we can write, m into 0. So m into 0 is equals to 0. It means the weight becomes 0 at the center of the earth. Okay, now let us see the next point. So the next we have, the weight is usually measured by the use of spring balance. So students, this is the spring balance with the help of which we determine weight of an object. This spring balance is enclosed in a metallic box, and on the metallic box there is a scale calibrated in Newton which gives the weight of a particular object. Whatever the object's weight we have to determine, we place that object here at the hook provided at the end of the spring. Then what happens? Whenever the object is placed here, the pointer starts moving. We have to wait so that the pointer stop moving. And when the pointer stop moving, fix at a certain point, then that certain point gives the reading of weight of this particular object. Now let us calculate weight of an object on the moon. So let us suppose that there is an object of mass small m, then its weight Wm on the surface of the moon is given by Wm is equals to mass of the object into acceleration due to gravity on the surface of moon, that is Gm. Let us say this is equation number 1. Here Gm is the acceleration due to gravity on moon. Again let us suppose that weight of the same object on the earth be We. Then we can write We in the same way, mass of the object into acceleration due to gravity on the surface of earth, that is Ge. Let us say this is equation number 2. Here Ge is the acceleration due to gravity on the earth. Now students, if we divide these two equations, then what we get? Wm by We is equals to m into Gm divided by m into Ge. Now here you can see m and m cancel out, and what we get? Gm divided by Ge. Again students, you know that Ge is equals to 6 times Gm. So what we can write here? Gm divided by 6 Gm. That is, in place of Ge we can write 6 Gm. So here again Gm and Gm cancel out, and what we get? 1 by 6. So from here what we can write? Wm by We is equals to 1 by 6. Or when we cross multiply, then what we get? Wm is equals to 1 by 6 We. Wm is equals to 1 by 6 We. That is, weight of an object on moon is equals to 1 by 6 the weight of the same object on the surface of earth. So this is the relation between weight of an object on moon and weight of an object on earth. Now let us suppose weight of a man is 600 Newton on earth, then its weight on moon will be Wm is equals to 1 by 6 times We, that is weight of man on the earth. Here it is given weight of man on earth is 600 Newton. So what we can write? 1 by 6 into 600 Newton. So it is equals to 100 Newton. It means if a man weighs 600 Newton on earth, then it weighs 100 Newton on the surface of moon. Now let us solve some problems. Here we have the first problem. Gravitational force on an imaginary planet is 6 times stronger than the gravitational force of the earth. Determine the value of acceleration due to gravity and the weight of an object of mass 50 kg on that planet. So here in this problem it is given that there is an imaginary planet such that the gravitational force on that planet is 6 times stronger than the gravitational force of the earth. Then using this information we have to find the value of acceleration due to gravity on that planet and also weight of object of mass 50 kg. So let us see the solution. First let us suppose G dash and G be the acceleration due to gravity on the imaginary planet and earth respectively. Then for an object of mass m, we can write the gravitational force on the imaginary planet equals to mass of the object into acceleration due to gravity of the imaginary planet, that is m into G dash. In the same way, gravitational force on the earth is equals to mass of the object into acceleration due to gravity of earth, so m into G. Again in this question it is given that the gravitational force of the imaginary planet, that is this m into G dash, is 6 times stronger than gravitational force of the earth, that is m into G. So according to question what we have, m into g dash is equals to 6 times m into g. So from here, m and m cancel out, and what we get, g dash is equals to 6 into g. Okay, so we can write g dash is equals to 6g, and you know value of acceleration due to gravity on the surface of earth is 9.8 meter per second square. So what we can write, g dash is equals to 6 into 9.8 meter per second square, so it is equals to 58.8 meter per second square. So this is the required acceleration due to gravity on the imaginary planet. Now we have to calculate weight of an object of mass 50 kilogram on this planet. So we can write weight of an object of mass 50 kilogram on that planet is equals to mass, that is 50 kilogram, into acceleration due to gravity on that planet. Acceleration due to gravity on that planet is g dash, which is equals to 58.8. So here we have written 50 kilogram into g dash. Let us put the value. So 50 kilogram into 58.8 meter per second square, which is equals to 2940 Newton, which is our required answer. Now let us see the next problem. If the distance between two objects is increased 4 times, then by how many times will the mass of one of the objects be changed to maintain the same gravitational force? Now students, you know gravitational force between two objects of masses m1 and m2, which are separated by distance r, is given by capital F is equals to capital G m1 into m2 divided by r square. Now here the separation between the two masses m1 and m2 is r. According to question, if r is increased to 4 times r, then by how many times either of these two masses m1 or m2 be changed such that the force will remain the same, that is F. So students, let us suppose if the distance is changed from r to 4r, then mass of the first object, that is m1, is changed to m1 dash so as to maintain the same gravitational force F. Then what we can write, F is equals to G. In place of m1 we can write m1 dash into m2 divided by, in place of r we have to write 4r, so 4r square. So it is equals to G m1 dash into m2 divided by 16r square. Again these two forces are same, so we can equate equation 1 and equation 2. So when we equate equation 1 and equation 2, then what we get, here we have G m1 m2 divided by r square is equals to G m1 dash into m2 divided by 16r square. Now here G and G cancel out, m2 and m2 is also cancelled out, and r square cancel out. Then what we get, m1 dash is equals to 16 times m1, this. So it is stated that if the mass of the object, that is the first object, is increased by 16 times, then the gravitational force will remain the same when the distance is changed to 4 times. Okay, now let us see the next problem. Here we have given, so that if Earth attracts two objects A and B placed at the same distance from the center of Earth with the same force, then their masses are equal. So let us see. Let masses of the two objects A and B be m1 and m2 respectively, and they are placed at a distance r from center of the earth of mass capital M. Then the forces of gravity acting on A and B be F1 and F2 respectively. Then what we can write, F1 is equals to G capital M into m1 divided by r square, and in the same way F2 is equals to capital G capital M into m2 divided by r square. Now it is given that F1 is equals to F2 according to question. So what we can write, G capital M into m1 divided by r square is equals to g capital M into m2 divided by r square. Now here g into capital M is cancelled out, r square is also cancelled out. Then what we get? m1 is equals to m2. Hence it is proved that if Earth attract two objects placed at same distance from the center of Earth with same force, then their masses will also be equal. So thank you students. Thanks for watching.